Hi there! In the last lecture, we have looked at the cases when we need to avoid recursion and when we need to use it. Now in this lecture, we will look at how to write recursive method for any given problems in 3 steps. We learned from our previous lectures that a recursion function calls itself repeatedly until base condition is satisfied. A function calling itself is very dangerous, as it is relatively less intuitive and may run into some runtime error if we don't treat it with extreme caution. So here, I will introduce you a 3-step approach that can make you confident enough to write your own bugless recursive functions. So as an example, I will use a mathematical problem which is called factorial. In case you don't know what factorial is, let me just give you a brief explanation. Factorials were used to count permutations at least as early as the 12th century by Indian scholars. It's a product of all positive integers less than or equal to n. Factorial denoted by n and exclamation mark. This notation was introduced by French mathematician Christian Kramp in 1808. We can calculate factorial only for positive numbers, and the factorial of 0 is 1. As an example, if you want to calculate a factorial of 4, the answer will be like this. 4 multiplied 3, multiplied 2, and multiplied 1. So how did we get this 4, 3, 2, and 1? It's coming from the definition that all positive integers less than or equal to n. So in our case, n is 4. So all positive integers equals to 4 and less than 4 are 4, 3, 2, and 1. So the product of these integers is factorial of 4. Now let's say another example. If we want to calculate factorial of 10, so how do we do that? Again, we start from 10 and taking all positive integers that are less and equal to 10. So we know that all positive integers that are less than equal to 10 starts from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So if we multiply all of these numbers, we are getting factorial of 10. So based on these points over here and the examples that we provided here, we can express the factorial of n like this. This is the base equation for factorial. Now let's see how can we find out this factorial of any given value using a recursive method in 3 steps. So the step 1 is recursive case, the flow. When we create a recursive function, the first thing that we have to do, we need to identify the recursive case. In our case, which is how a factorial function is defined using factorial functions. So we have identified that the general expression for factorial is like this. So how can we write this recursive function to have a factorial on both left and right sides of this equation? So if we look at this carefully, we can see that this part is over here can be expressed n minus 1 factorial. If it is not clear, let's calculate the factorial of n minus 1 separately. So the factorial of n minus 1 is calculated like this. N minus 1 multiplied with n minus 1 minus 1, then multiplied with n minus 1 minus 2, then it continues until we reach 1. If we do some calculation here, we are getting the value over here. And you see that this expression over here is equals to this expression. So this means that we can change our function something like this. N factorial is equal to n multiplied with n minus 1 factorial. In this case, we have successfully found a recursive case, which means that on both left and right side of equation, we have factorials. Now we have identified the recursive case. Let's switch to Visual Studio Code to develop this case in Python. So here I will create a function, factorial, which takes n as a parameter. then it will return the expression that we have over there, which is n multiply with n minus factorial, n minus 1 factorial. So this is our function for this expression over here. As you can see, we have just developed the recursive case in the Python. So our first step of identifying recursive case is done. In this code, you can see that our factorial calculation is almost done. You might be thinking that this function over here is enough for calculating factorial. But there is a bug in this code. Let's try to find it. Let's run this function for factorial 3. So here I will put factorial 3. So to see what's going on, I will just add here print function which will print n, because otherwise we will not see what's going on. So if I now run this function, we see that Python raises error saying that maximum recursion depth exceeded while calling a Python object. This means that we have a limitation to keep number of methods in stack memory. Basically, it's possible to increase the stack memory. We can, for example, here, we can import sys, and there we can increase stack memory, import sys. Then if I do like this, sys set recursion limit, in this case you see that it's 992, but if I do it, for example, like 10,000 and rerun our application, we see that it comes here 9,992. So we can increase the stack memory, but here our goal is not to increase stack memory. Our goal is to prevent this situation. If you go back here, you see that our function get called 10,000 times and never stopped. Because the recursion limit in Python is reached, that's why it stopped. So this means that there's a bug inside our function. So here we see that the function keeps calling itself without stopping. This will lead to a system crash if we implement it in an application. So the question is, how do we need to prevent this case? So to prevent this case and write bugless code, we need step 2. So let's see what's step 2. Step 2, base case, the stopping criterion. As you remember from previous lectures, we need a base case to prevent infinite loop. So here, we need a base case for our recursion function as well, where it stops calling itself. So how can we do that? As we said in the definition of factorial, that factorial of 0 is 1, and it's obvious that the factorial of 1 is 1. So as a base case, we can use these conditions over here. So let's return to our code. Here, I'll just delete this one. Let me just delete this one as well. As a base condition, I will write an if condition over here. If n in 0 or 1, then we will return 1. Otherwise, the function will call itself recursively. So here we will put like this. So now we have added base case in our function. So if we rerun our function for factorial 3, we will see that this error that appears here will be disappeared. So I'll print the value from here as well, print function to here, to see what is the factorial of 3. So if I rerun this code, you see that it calculates the factorial of 3 as 6. Let me just clear here and put, for example, factorial 4 here and rerun our code. You see that it calculates No, I haven't saved this, that's why it gives me 6. After every change, you need to save the file because as you see that I have a sign here that I haven't saved. If I click save and rerun this function, you'll see that the factorial of 4 is 24. Now here one more time, you might think that we are done with our code in 2 steps because our code works the way as we want. So why do we need third step? So here, I want you to pause the video, think if you can find what's missing in this code. Okay, let's see what's missing over here. The most important thing to consider when writing a recursive function is making sure that function stops for every possible argument n. So here, we need to identify in which case it doesn't stop. So for this case, we have step 3. Step 3 is unintentional case, the constraint. We have base condition for our function, which is for when n equals 0 and when n equals 1. And our recursive case calls the function itself with an argument n minus 1. This means that the function will reach a base case only if factorial n starts with a non-negative integer. So from definition of factorial, we know that it is calculated only for positive numbers. So if we run our function for -1 and 1.1, what will happen? Let's rerun it and see what's happening. Okay, if I put here -1 and save it and rerun it, you see that again we are getting the error that we got before, which is maximum recursion depth exceeded in comparison. This means that our function again inside infinite loop. So we need to prevent this case as well. While there are different methods to achieve this, we will use a simple assertion method in Python that throws an error if n is not a non-negative integer. So if you don't know how the assertion method works in Python, in the resource section of this course, I have attached a PDF file which shows the logic. Basically, what we are going to do here, before if condition, I will write assert case, which checks n is greater and equals to 0, and the second case is n has to be integer. So an integer equals integer. Otherwise, it will raise an error. So the error will be like this: the number must be positive integer only. Basically, this line of code makes sure that n is a positive number and it's integer. If not, it will throw an exception that the number must be a positive integer only. In other words, we are forcing the argument n to be a non-negative integer. So now our function is ready. So if we run the same case for this function with -1, you will see that it gives another error saying that number must be positive integer only. This means that our function is not anymore inside infinite loop. So again, if you run this function for 1.5, you'll see that the same error comes over here. For example, if we run our function for 10, we need to calculate 10 factorial. You see that it's calculated as the way that we calculated. So with this, we have implemented last step successfully for our recursion function of factorial's number. To make things more clear and more understandable, let's run this function for any integer number and see what's happening behind the scene. So I will just copy this function from over here and put it over here. For simplicity, let's run it for when n equals 4. If we run this function when n equals 4, the control comes to the first condition where it says n is greater and equals 0 and n has to be integer number. So we see that 4 is greater than 0 and it's an integer number. So everything okay with this case. So it will continue to the next case. In the next case, we are checking that if 4 is 0 or 1. We see that 4 is neither 1 nor 0. So the controller comes to the else statement. What's the else statement? It says n multiplied with factorial n minus 1. So what's right now n? It is 4. So n is multiplied with the return value of factorial n minus 1, which is, in our case, 4 multiplied with factorial 3. So we don't know the return value of factorial 3, which means that our controller will call this function recursively. So the controller once again goes to the first line. Here again we check that whether 3 is greater than 0 and if it is an integer number. And we see that all cases are okay here. So we continue to the next if condition. Here we see that n is not 0 or 1, which is 3. So the controller will continue to the else condition. Now one more time in else condition, we have a return value which is n multiplied with factorial n minus 1. So in our case, n is 3. So it will be 3 multiplied with factorial 2. So here one more time we see that we don't have any return value for 2, which means that our function will be called recursively once again. So the controller will go to first line again. Here we don't have any problem for 2 again because 2 is an integer number which is greater than 0. And it will continue to the next condition. And in the next condition, 2 is not 0 or 1, which means that this controller will go to the else condition as well. In else condition, we have n multiplied factorial n minus 1 more time, which means that in this case it will be 2 multiplied with factorial 1. So this means that one more time we will do a recursive call to our function. So when we call our function with parameter of 1, so the controller one more time goes here. It checks that 1 is greater than 0 and it is integer number. Then it goes to the next condition. Here we see that n is equal to 1, which means that this function over here will return 1. So the return value of this function is 1. So if you have the return value of this function, we can easily calculate the return value of this function over here, which is the factorial function taking the parameter of 2. So the return value of factorial 2 is 2 multiplied with the factorial 1. So we know that factorial 1 is 1. So 2 multiplied with factorial 1 will be 2. So now we have an output for this function. So the factorial 2 is 2, which means that we can calculate the factorial 3 because the return value for factorial 3 is 3 multiplied with factorial 2. So in this case, the return value for factorial 3 will be 6 because 3 multiplied 2 is going to be 6. Then from here we know that return value for factorial 4 is 4 multiplied with the return value of factorial 3. So we have calculated the return value of factorial 3, which is 6, and 6 multiplied with 4 will be 24. So the factorial for 4, so this is how we recursively find the factorial of any given number. Here I try to show you that when you call a factorial function recursively, what's happening behind the scene. And behind the scene you saw that every time the function calls another function which is 1 or less until it reaches the base condition that we have a return value. If we don't provide the base condition over here, our function will be inside infinite loop. Now in this lecture we have introduced you how to write a recursive method in 3 steps, and hopefully you understand it. And I gave an example of factorial using these 3 steps to write a